All right, the next application of double integrals that we're going to look at is one of my favorite, actually. Have you ever seen one of those weird little bird toys that balances on its beak? You can just set its beak on the table and the whole thing will sort of balance there. That has a connection to what we're going to do. So we've got this lamina, this really thin sheet, and it looks something like this. Unfortunately, as I was looking at my picture, mine wouldn't look like that because it looks kind of twisted. But please imagine that this is a flat, very, very thin sheet. I'm going to be obsessive compulsive and highlight the whole thing on video, even though I should have done that before. Can't help it, sorry. Okay, so I've got that sheet. And what I want to do is I want to be able to balance it on a needle. And so obviously if I put the needle over there, it's not going to balance. You can see somehow it's going to have to somehow be in the center. But the problem is when we think of balancing, we're assuming constant density. And that may not be the case, right? Our density is actually changing depending on where you are. So you can't just balance this thing visually. You have to take into account the density as well. And so we need a way to find the center. So let's imagine that the center is right here and that we've got this thing balancing, and we'll call this x bar, y bar. So that's what we're saying the center of mass is. The center of mass is going to be x bar, y bar, and we want to know, how do we find that? If I have this lamina, I know its density function, I can compute its mass, but I really want to be able to balance it on a needle because that's what I like to do. How do you find x bar, y bar? Well, here are the formulas. It turns out that the x-coordinate for the center of mass is just 1 over the mass of the lamina times the double integral of x times rho of xy dA. And then the y-coordinate is very, very similar. Y-coordinate, y rho, x-coordinate, x rho. Hopefully you see the very clear pattern there. There's a lot more that can be said about these integrals. You may have heard about moments, especially you engineers. You can think about this part of the integral as the moment about the y-axis, and this can be the moment about the x-axis. I'm not going to get into that other than just to mention it in passing, but those are formulas you'll need to be aware of, and I thought I would do an example with you. In fact, let's just do the previous example that we did before. So let's go up. I'm going to use my copy function, and I'm going to copy my picture because I don't want to redraw it. So copy, scroll down, paste, here we go. Oops. So let's find the center of mass of our region R if, again, rho of xy is just x. So from before, we know that the mass of R is 1/3. That's what we came up with before. And so now I'm just going to use these formulas, right? X bar is just x times rho of xy. I'm looking up here. That's the formula for x bar. I'm just going to write that down. 1 over 1/3 is going to be 3. So that's where the 3 is coming from outside of here. So x bar is 3 times the double integral over this region R of x times rho of x. Well, that's just x squared dA. And just like before, we'll switch this thing to polar, and we're going to get 3, 0 to pi halves, 0 to 1, r squared cosine squared theta r. So I'm going to go ahead and write that as r cubed cosine squared theta dr d theta. The only really difference in this integral, computation-wise at least, is that you have this cosine squared. Here I'm going to want to use one of my formulas to reduce that power. I'm going to convert cosine squared of theta to 1/2 1 plus cosine of 2 theta, and that's how I'll be able to compute it. And I leave it to my trusty, dependable Calc 3 students to compute 3 pi over 16 as the answer. And so please check that. If you don't get that, go back and check it again. Similarly, it's just almost the same process for y bar. You're going to get 3 again, double integral over r of this time y x dA. All right, so we'll switch to polar. 0 to 1 is what r goes. 0 to pi halves for theta. I'm going to get a r cubed when I throw in the r in the end, r cubed. And then I'm going to have a sine theta, cosine theta. Ooh, I like this one better. Pause the video and figure out why this is better than the last one, easier. It's easier because you can just do a u substitution. So really not a bad integral to compute. And again, I have full confidence in you guys that you can work this out yourselves. Please do that. Pause the video, work it out, and get 3/8. And so the point is the center of mass is, well, x bar, which was what, 3 pi over 16, comma 3/8. Now, just to be very clear, please don't conclude that the center of this circular shape is that point. That's not what we're saying. We're saying the center of mass, I think I just said the center of the shape, I meant the center of mass. We're saying the center of mass of a thin sheet with this shape and this density function is going to have that center of mass. If you change the density function, you're going to change the center of mass. So you can have the same shape and have a different center of mass depending on density. That somehow seems clear, but I just want to make sure that was communicated. I think we will stop this section here. You guys are ready to do the 12.4 homework problems. Good luck with those, and we'll pick it up in 12.5.